Hi everyone. So my name is Chul Lee. I tried to speak up, but if I can't, then yeah, my apologies. So today I'm going to talk about how we are using Spark at MyFitnessPal together with Hesam, and then I'm going to start with some kind of quick intro of our company, and then especially in the context of UnderArmour, because we got acquired this year. So after I'm done with that, I'm going to talk about some data assets that we have. And then after that, we'll talk about Spark at MyFitnessPal, why, and then some quick summary of some use cases that we have. And after that, so my part is actually going to be somehow boring, and his part is going to be more exciting because he's going to do some kind of deep dive into details of how Spark is being used at MyFitnessPal. And then after that, we're going to have some kind of QA session, so feel free to ask questions. So what is MyFitnessPal? So how many of you guys have heard about MyFitnessPal? Okay, so pretty good number. That's good. So we are a simple and effective health and fitness tracking tool. We are one of the best-known health and fitness apps. And then we have this huge reach of, more than 70 countries. So we serve like a pretty international kind of user base. So and our users have been really loving our app, right? So because of this, we have a very massive and very friendly community of users, which is more than 90 million users, and this number is growing, right? One thing that we are very proud of is, so we have one of the largest food database, and then this is very interesting kind of thing in the sense that we have been accumulating this big database or knowledge base of food items, and first time in the history of mankind, right? And then this is really amazing, right? So no one was able to really archive or track this database of food items. And then MyFitnessPal actually did that. And then luckily enough, because of this, we have been able to accumulate over 7 million food items, right? That translates into 19 billion food entries. So this is a kind of very interesting database of really being able to track how users and how people are really consuming foods, and then what kind of diet patterns they have and so on. That's very interesting, right? So as I said before, MyFitnessPal joined UnderArmour in March of this year. And then after that acquisition, we became more interesting because now, thanks to UnderArmour, our reach has broadened, right? And then now we're talking about 150 million registered users across UA Connected Fitness, because UnderArmour bought 2 more apps before MyFitnessPal, and then together with the MyFitnessPal user base, and then the rest of other apps, we're talking about 150 million users, right? So this is an article that talks about how UnderArmour is trying to become a tech company, right? As you might know, UnderArmour is really emerging brand, really going heavily after Nike, right? And then getting a lot of traction, right? But at the same time, UnderArmour is trying to become a tech company, and then this is why UnderArmour bought different apps, and then that's why we became part of UnderArmour family. So what does it mean? So this means we have a lot of data, right? In various formats, right? So that means because of MyFitnessPal, we are pretty rich in terms of food and nutrition data, right? A lot of food entries, a lot of food items, I said before, and then 38 million recipes, right? Which has been generated by over 90 million MyFitnessPal users, as I said before, right? But at the same time, as I said before, because of other apps, we have a lot of workout data, right? So that meaning running data, right? We have a lot of time series data. We now have music data with workout, right? We had walking data. We have activity data. We have sleep data. And then we have a lot of data that we'll be able to collect, through our partnerships and so on. So we have a lot of data, right? Workout data in particular. And on top of that, Under Armour has been a retail and e-com company for many years before we came aboard. So therefore, like Under Armour actually has a lot of product transaction data, and then in addition to those transaction data, we have a lot of user preferences on different clothes, shoes, wearable devices, and so on, right? So you can really see the wide spectrum of different data assets that we have, right? So this is very exciting. So why Spark, right? There's several reasons why we started considering Spark as an option for our data warehousing. So number one was data volume, right? We have a lot of data, right? So we had to think about ways of processing that volume of data, right? And at the same time, we had to deal with all kind of different kind of data, as I said before, right? So we had to find a tool for that, right? So then in that case, you pretty much have two options, right? So and then more traditional way of doing that would be Hadoop, right? That's what everybody has been doing, right? The other option that we had was Spark. As a matter of fact, we ended up really using both. So we used both Hadoop and Spark, right? But the reason why we started looking into more Spark was our challenges were a little bit different from traditional sense of MapReduce type of thing, and then you just store the data in your Hadoop cluster, and then you do typical ETL stuff, and then on top of that you do some kind of data processing. Why? Because we had to deal with a lot of complex and diverse argument needs, right? More specifically, we had to deal with in-memory state aspect of data, meaning when we are doing a lot of data processing and then machine learning stuff or development of data products, we had to persist data in memory, right? And then as you might know already, when you're using Hadoop, right, it works when you're using Hadoop as a simple storage engine and you store just data. But when you want to use Hadoop as a computation engine, it kind of works, but it doesn't work all the time, right? Especially when you're trying to hold your in-memory state, right? So one example of that could be, well, when you try to run LDA stuff, right? Sure, using Hadoop, you can do that. But each time that you're running your LDA computation, then you have to really deal with a lot of disk, I/O bottleneck, because you can't persist data. Therefore, you have to store that persistence in disk. So probably that's not ideal, right? And there are numerous use cases for why in-memory state kind of machine learning or your data processing are desirable, right? At the same time, we had this kind of speed requirement, right? So because we're in this domain of health and fitness, right? So it's not true all the time, but most of the times, faster data processing will result into a better customer satisfaction and product experience, right? So for instance, if you want to provide nutrition and running insights, ideally you want to react as quickly as possible rather than just wait a week, and then after a week, right, the value of your insight will be really, it's going to be very diminished, right? So we want to have faster processing there, right? Another example, which is more in the context of retail, would be if you want to run some marketing campaigns, right? And then obviously you want to be very reactive, right? The moment that somebody is purchasing something, and that moment we want to really target and that user, and then provide some kind of marketing campaign, right? Depending on some transaction data that user has provided, right? So this is why we started looking into a Spark, right? I'm not saying here that Spark is the only way of really solving all these kind of problems, and I'm not saying that Hadoop is going to go away, right? So, but what I'm saying is for our own purpose, Spark has to be very effective, right? This is why we are here to share some of our experiences. Okay, so as I said before, we are using Spark at MyFitnessPal, and then we are expanding our use cases. The first use case that we had via Spark was machine learning, right? So this was quite interesting because if you again think about the evolution of Hadoop infrastructure, right? So the evolution of Hadoop infrastructure has been data warehousing first. So you store data first, and then you build a computation engine on top of Hadoop, right? But from my understanding, like one thing that was very interesting about Spark was like Spark was born as a computation engine, right? And I know we have some Spark guys here, so correct me if I'm wrong, but that was like kind of the emergence of the birth of Spark. So it started as a computation engine. So we had this like luxury of really bypassing this data warehousing aspect of Hadoop, and then like directly start doing computation aspect of data, right? And that's why like the first application that we had for Spark was machine learning, and we felt that was kind of natural fit for Spark, and that worked very fantastically for us. And then that's when we use ML Leap as a like a way of doing machine learning. And then in that process, we got a lot of help from Databricks and then some inventors of ML Leap, right? The other use case of Spark at MyFitnessPal has been advanced data processing. Again, I'm saying like I'm putting like advanced like in quotes, because like using Hadoop or any kind of traditional data warehousing or any kind of databases, you can do data processing, right? So I don't think it's true that some people I don't agree with some people who claim to say, oh, like Spark is going to really like override like Hadoop and it's going to replace Hadoop, blah blah. I don't believe that, because I mean Hadoop has its own place, right? Because for simple data warehousing, definitely like Hadoop will be useful. But when you want to start doing advanced data processing, right? I think Spark is definitely efficient because you can store like again your state in memory, right? And then you can persist, right? And then that means like once that you want to do advanced data cleansing, then persisting that state in memory is extremely helpful. And an example of that could be if you want to do some kind of clustering stuff, then you want to maintain some your clusters in memory, and then for that kind of purpose, then doing in-memory data processing is definitely helpful, right? Advanced data exploration analysis, same thing, right? Like, yeah, you can just claim that, oh, like you can do aggregations and you can really store these aggregators like using Hadoop, true, but if you can persist those states via memory, right? Faster, more efficient, and then more scalable, right? Some ETL jobs same, right? Like you can like your ETL jobs using Hadoop, right? But if you want to do like a lot of batch processing with some states kind of persistence, then probably like a Spark is the right way to go. And then that's kind of the area that we're exploring, right? Finally, we have been using like Spark for product and decision science, right? Again, I don't think this is really mandatory because you can just same with Hadoop infrastructure or other like data infrastructures, but sometimes you need like speed, right? And then sometimes you need like in-memory persistence again, right? Then for those kind of use cases, definitely you want to really have these tools handy so that you can really like have a very quick like turnaround, like run like product and decision sciences, right? So this is the way that we have used Spark at MyFitnessPal, and I think Hesam is going to talk more about.
All right. Hello, everybody. My name is Hesam. I'm a senior data scientist in MyFitnessPal. Today, I'm going to talk about a sample use case of using Spark for our data processing, which is verified food. It's a common feature among our users because we've had these requests from users for a long time to come up with the most accurate subset of the foods that we've had in our database with respect to the nutrition information. And the reason for that is we, based on the crowdsourced data that we've collected from users, we have all sorts of duplications and inconsistencies among our data set. For instance, we have like McDonald's McChicken sandwich in lots of different formats, especially if we consider different misspellings. Like the first example, there are several items referring to the same entity in our database. And from the nutrition data, it's kind of inevitable to have inconsistencies even for the items that are referring to exactly the same thing. For example, These are the two sets of nutrition facts for apple from two different resources, but we can see that the nutrition information are different from each other. So this is very important in our user search experience, because once we present the search results, you can see that, for example, for the item like tangerine, user can find all different sources of calories, and like it might bring a lot of confusion to the users what item to select. And more importantly, they may not have much more confidence to the existing nutritional facts. So that was the number one motivation for us to go after this really accurate subset. The other one was the existence of a lot of private foods in our database. By private, I mean the food items that users can just create themselves and use themselves, and these items are not necessarily searchable. So based on what described earlier, we have around 7 million food items which are public and searchable, but we have a lot more food items that are private. And before doing this project, we hadn't used this huge set of foods for any purposes. So that was a very good opportunity for us to start looking into these private items and having an aggregation process to compute the most accurate nutrition information. So the goal that we were trying to target was to have this kind of search experience such that you can see this green check mark for the items whose nutrition information has been verified by this process. And this is very ideal search experience that we were going after. And the solution that we presented was based on a process in Spark, where we decided to use implicit and explicit signals from users. So there are several types of inputs from users that we could employ in order to compute this accurate set. The implicit signals are the number of times a particular food item has been logged, and that would probably tell us something about the correctness of the nutrition information and also the convenience of the serving sizes for the food item. And also, if users have created a lot of private foods with exactly the same name, the same nutrition information, so that would tell us that they probably are referring to the same resource. And that's kind of like a trustable resource for us to make the analysis based on. And the explicit signals are some of the signals that we've gathered over time, especially, for example, if the users have confidence on the nutrition information, we can get some confirmations. And we can consider the number of confirmations for a food item as a very strong signal. But unfortunately, we don't have many of these types of signals. It's kind of sparse. And another thing is the public and private foods, which are kind of treated in a different manner. So these are all the signals that we were dealing with to come up with this process. So any question? Yep.
So as far as the really standard foods, right, anything with a barcode on it, is there a particular reason that you would just take an image of the entire nutrition label? I mean, it's all like very standard font text. It's black, white, high contrast. And why not just run character recognition on that and like pull the data from the nutrition label?
The question for the camera. Oh, okay. So the question was, since we already have the feature which is barcode scan, why don't we have the feature for the users to take a picture of the nutrition facts and just do an OCR on top of it to get the nutrition fact? But the answer to this question is the most problematic examples are like Apple or McDonald's burger, the things that they don't have neither barcode or the nutrition facts on top. So
But is there a particular reason why for the things that have nutrition labels?
for those kind of stuff, we have a huge set of imported food items. That's why we compared the barcode with the one that users scan. And we make this comparison, so we already have the nutrition information for the ones that are that have a barcode attached. So we don't need to like do an OCR on top of them to just get the nutrition information. But that was a part of like a subset of the all the verified foods that we have released. So the subset that I'm going to talk about was the ones that we came up with by processing the foods in our database. So as mentioned earlier, there are several benefits of using Spark for our data processing. We had different sources of data from different types, and having them all together and doing some kind of like joins on top was very convenient in Spark. And also there were some libraries in Spark being implemented like MLlib and graphics. And that was very good for us, and that was very convenient for us to use. And also a lot of processes that were parallel in nature could be executed in a very fast manner. So in the next few slides, I'm going to walk through the whole process of finding this subset of verified foods. The data that we were dealing with was a combination of all sorts of data, from nutrition information, from the foods, the string of brand description, the user IDs, like who's created the foods, and also the signals that I was talking about earlier, which was the number of times each food has been logged, and etc. So in Spark, we could just simply register all these tables together, and we could make a join in a very fast manner. And by the end of the day, we had a class defined called food, and it had all different fields that we were looking for. For example, the string of brand and description, the nutrition facts like calories, fat, protein, etc., and also the signals that were coming from users. So the RDD that we were dealing with afterwards was just a simple RDD of the foods. So that was the natural way of dealing with this huge data in Spark. So in order to make the process more accurate, and since we were dealing with user input data, we had to run some kind of string processing on top. And this string processing is very simple string manipulation, like removing the punctuation characters or duplicate words, and also sorting the words in the brand and description based on the first character, because in several cases the food names are referring to the same thing, but the words are kind of in different order. So on top of this food RDD, we had to run this normalized brand plus description. And what we'll end up with after this step is an RDD of key values, which are a string, which is the normalized brand and description plus the food item itself. This was very interesting for us because after this, we could apply the simple function implemented in Scala, which is group by key, and to find all the items that are having pretty much the same name. So that was probably the most important step that we could take care of for our aggregation process. So there are some instances in this picture. For example, coffee, mocha, Starbucks is a collection of all foods that are actually referring to the same entity. And the same example for like McDonald's, nuggets, and etc. And if the names are kind of weird, it's because the words are kind of sorted. So they may not make sense. So after this cluster identification, we had to find one of these members of each class that is the best representative. So the definition of best representative is really tricky, especially when we're dealing with user crowdsourced data. But based on the signals that I talked about earlier, like the number of times each of these members have been logged or have been confirmed by the users, and whether or not this food is public or private, we decided to pick the one that has the highest score. And this score is computed considering all different signals. So that's why this particular item is colored in green. And from now on, we are trying to get the nutrition information from this cluster representative and to make the nutrition information as complete as possible based on the rest of the items in the cluster. The one thing that I want to emphasize is that these clusters may be good enough, meaning that we have enough number of members in each class, and we have some level of confidence to the nutrition information that have been aggregated from each cluster. But in some cases, this cluster may not incorporate into generating a verified food. So for the items for the classes that we have a verified food, so for instance, this green row was the item that was picked as a representative, but having the nutrition information even from this representative, it may not be trustable. And we decided to go through the rest of the members in this class and fill up the gaps. For example, if the fat value is missing in this representative, based on some kind of voting and aggregation over the different members of this class, we decided to fill the gaps and return the most accurate and most complete set of nutrition information. So one step that was kind of mandatory for us to take care of was to get rid of the duplicates. So after running this process and after computing the verified foods, for example, we realized that we have, for popular items, we have different versions of the verified foods. And they were all promoted from different clusters. For example, for McDonald's chicken nugget, we have different types of strings. And not all of them are necessarily end up in the same cluster based on the string processing that we presented. So one important step to take care of these duplicates is to run a dedupe process. And we decided to run this dedupe process on top of the clustering step. And that's why I have put the step 1.5, because it's between the clustering and the nutrition aggregation process. So in order to run it, we decided to do it on top of the clustering. For example, if we have a cluster for coffee, mocha, Starbucks, and we have another population, which is probably a smaller population, but they have coffee misspelled. So they're referring to the same entity, but with the string similarity, it's not really easy to find these instances. So we decided to have this deduplication process, and once we figure out they're actually referring to the same entity, we decided to compute the union of these clusters and generate a bigger class. And with doing so, we can benefit from two advantages at the same time. First, we can get rid of all these misspells and the words that are actually duplicate. And also, we will have larger classes, meaning that we will have more members in each class. And more members provides more confidence towards the nutrition aggregation process. So that's an important step that we had to take care of. And in order to solve this, we went after a pairwise string similarity comparison between all the cluster representatives. But as you can guess, this is not the most efficient way. And that was quadratic with respect to the input size. The running time was a lot. For 1 million input foods, the running time was kind of reasonable, like 5 minutes. It took around 2 hours for 5 million items. Still not too bad. But when we wanted to try for 50 million, it could raise to more than a week. We didn't try to run it. We just estimated that it's going to take for a week at least. And we're not that patient to have this running time, although this process was extremely simple. And the main downside with this pairwise comparison was that it's not parallelizable, because we cannot like separate out different computation parts, because everything is so relevant to each other. In order to overcome this issue, we made use of locality sensitive hashing, which is a well-known technique in machine learning community. It's abbreviated as LSH. So LSH is a method that, in a probabilistic manner, predicts the members that are with high confidence they're belonging to the same bucket or to the same cluster. For instance, in this case, given all these cluster names, LSH could help us identify the candidates of being duplicate. And of course, since the process is not deterministic, we will have a lot of false positives and false negatives. But considering this speed of this process, that was a huge gain for us. And the fact that the whole population is divided into different buckets was very appealing, especially when dealing with the Spark, because we could parallelize the process for each bucket and run a string, pairwise a string similarity within each bucket only. And this process was a lot faster, as you guys can guess, and it took less than 5 hours for the entire data set. So considering the 1 week versus 5 hours, that was a huge time gain for us. And actually, we used the LSH code in Spark, which is available in the GitHub, and that was very efficient for us. So on top of the nutrition aggregation and extracting the verified foods, we had to add another layer as a post-processing step. The reason was we ended up with some verified foods where you can see that they only have the calories information. And the reason for that is most of the users don't really care about the macronutrients or micronutrients. For example, fats, carbs, sodium, etc. And they only add the calorie for the food that they're trying to log. So we ended up with several examples like that. And since there is a relation between the macronutrients and the calories, we decided to add another post-processing layer on top of the verified foods. And we applied some very simple rules on top. One of them was having non-negative nutrients. For example, we realized that several verified foods were called breastfeeding with minus 500 calories. And I'm not sure if it's correct or not, it's accurate, but from the user's experience, it's not very appealing to have this item and have a verified mark on it. And another sanity check was the relation between all different fats with respect to the total fat, and the summation of all should be less than or equal to the total fat, and the same for the carbs, sugar, and fiber. And the last one, which is a little tricky, is the relation between different sources of calorie with respect to the total calorie, meaning that the total calorie should be pretty close to the weighted summation of carbs, protein, and fat. And here is a snapshot of this last sanity check. On top of the verified foods, we can see that the calories, protein, carbs, and fat have been retrieved from each of these verified foods. And this relation has been used for filtering the ones that are, filtering out the ones that are not satisfying this rule. And you can see that the 10% margin has been added for this equality constraint. And that was it. So by the end of the day, since most of our users are pretty obsessed with before-after pictures, I'm adding this before-after picture before having this feature and afterwards. And you can see that only the items that are referring to tangerine and we have the most confidence of are marked as green verified items. And the rest of them are pretty much the ones that we don't have much confidence. So users are gonna much easier select the items that they're looking for. And that was it. That was a very interesting application of Spark in our database. And if you have any question, we will be happy to answer. Right?
Do you also take serving size as a part of your cluster calculation? If it's 16-ounce Starbucks coffee,
Right.
if it says it's 200 calories, and if Starbucks coffee of 8 ounces, it says 100 calories, do you do a post calculation to say 8 ounces?
Oh, OK. Oh, you mean for different serving sizes?
Yeah, you rely just on user information or also do some post calculation to come up with accurate calories?
Sure. If I understood the question right, the question was if we consider different serving sizes for the items that we were trying to aggregate for the nutrition information. Is it correct? So in that case, since we only considered the ones that are having the most agreed upon calories information, the chances are the serving sizes for these items are pretty much the same. But we actually decided to pick the serving size that is most dominant among each cluster. So within the items that are having the same calorie information, we decided to vote on the serving size that each item has. So we had this kind of aggregation process for both calories and serving sizes. So by the end of the day, we are pretty sure that this item with this serving size has this particular calorie information. Yep.
Was there any success case in the MLab clustering libraries doing this clustering? Is it the dimensionality is off the charts?
It wasn't like a speed issue for us. The reason that we actually did this simple group by key for clustering was that we wanted to only put the items in the same class that we are 100% confident. Because for any clustering algorithm, there are a lot of inconsistencies or instabilities, and we are not 100% sure that they're not going to be false positives or false negatives. But in this particular example, we wanted to just reduce all the items that are having pretty much the same name. So that's why we use that. And we employed this deduplication process on top. But another alternative was, for example, to use the clustering or K-means clustering, for instance, in MLlib. That was another alternative. But we tried to be more conservative.
So were there difference in clustering? So even though we basically integrate something, what we're doing here is unification is of the clustering protocol.
Any reason why you're using the class RDB?
Okay. The reason that we used that was we actually implemented. Sorry, the question was there any specific reason for using RDD versus data frame? We did this project like in January, February last year, and we didn't have like the data frame. So that's one alternative for us to migrate this. That's a good question.
And you mentioned that you guys have been like kind of with like different data sources. So I was wondering like what kind of like different data, like are you using like devreal or MyFitnessPal, like what kind of data sources?
So yeah, the question was how many data sources we had, what was the type of the data that we were dealing with. So we had some data living in S3. One was, for example, the Parquet file was one format. We had CSV files coming in. We had some data in TX file. So and also, as far as I remember, we had data in ORC tables. And like aggregating them all into the Spark was very convenient because we had like the tool for doing that.
Is there like JDBC something to worry about? You guys have like high also?
Not for this project, but for other use cases, we have like Hive tables that we need to aggregate. Yeah.
Is this algorithm theoretically that you handle a case when the UI then gets more information within the same cluster? Do you rebuild the data?
That's actually the goal. It's in its current form, it's not, but we have the cluster information being stored, and we have the information and the signals coming from users that what verified foods has been logged more compared to the others. And with respect to these items, we can just make some improvement to the algorithm with the user information. It hasn't been implemented, but we have the infrastructure to employ that, for sure.
Do you keep your original data before you deduplicate it? And if you do, how do you store that? Or do you just need to
The question was if we stored the data before deduplication or we just didn't. So we actually didn't store it. We had the whole data after clustering in an RDD. And once we deduplicated the data, the algorithm for doing that was to just merge these clusters. So we didn't lose any information. We just reassigned the cluster, for example, for the guys from this misspell version, to a new cluster representative. So we didn't lose any data, we just changed the cluster.
Did you measure the accuracy of clustering?
The question was if we measured the accuracy of clustering. The answer is, since we didn't use like machine learning based clustering in this case, it was like deterministic. But if you mean the LSH, for the LSH, the accuracy was around 75% or so, meaning that 75% of the times that like a bucket was detected by LSH, it was actually a true duplicate. But for the general clustering algorithm, since we only use this group by key operation, it's kind of deterministic. There's nothing to be worried about. It depends on the string normalization, for sure.
Kind of following up on that question, did you measure the performance of this at the end of the process? Like, for example, did you have humans go through and how they would do some data?
So the question was if we had some evaluation on top of this process. So are you asking about the correctness of the nutrition information of the data, or you just other metrics compute on top?
I suppose whether customers were more satisfied with the results after they trust the verified data, or how do you measure that?
That's a very good question. That's actually, we haven't looked at the metrics yet, but we would definitely expect the users to, I mean, for example, time per log or search per log to decrease significantly, but we haven't measured the stats yet. But that's a very good question.
How do you normalize for the disposition of a user clicking on a verified item versus a non-verified item?
Can you repeat the question? What do you mean by normalization?
So say a verified item might have a particular bias associated with it. How do you normalize for that?
Since the question was how do we normalize the user signals for verified and non-verified foods. So it's kind of a follow-up for the earlier question. Since we haven't looked at the metrics yet, that's a valid concern because users might be more biased towards verified foods versus non-verified. It's like the first rank results in the general search engines. So in that case, we haven't thought this through, but that's one of our concerns. But in general, we decided to not to rank, rank the verified foods too much higher compared to the non-verified items because we didn't want to mess up with the users' usual experience. So that was like another concern. Yep.
Talk about the input to your hash number.
What part, sorry?
The input to your hash number.
Oh, okay, sure. That was a good question. The question was a little bit more details into the LSH algorithm. If you go through this GitHub link, you can realize that this LSH algorithm in Spark has been implemented for integer values. And the main concern for us was how to make this transformation from string features to the integer features. And actually, the features were sparse vectors of integers. So in that case, we created trigrams for the characters of the existing in the strings. For example, if we have coffee, mocha, Starbucks, we consider all different trigrams, tree-length strings appearing, and having a universal vector, we specified we counted up and down the number of times it has appeared. So we ended up with sparse vectors of integers. So that was like a natural input format for the LSH, and the output was given this index. What is the bucket index that is found from the LSH algorithm? The vector was the entire set of possible trigrams. For example, starting from AAA to ZZZ. And since that's a huge vector of size, I think 17,000 or so, only a few of them are non-zero. So that's a sparse vector. And that was exactly what this LSH code was looking for, Spark. Sure.
Does that bias longer
The question was using this transformation if we bias the longer phrases too much. The answer is if we have a longer phrase and there is another longer phrase that is pretty similar to that, so that's natural to end up within the same cluster because we have a pairwise comparison by the end of the day. And if we have a large phrase and we have another small phrase, they're definitely not referring to the same entity, and it's appealing not to end up with the same bucket.
Yeah, so there's almost a higher bar for smaller phrases than the.
That's true. I mean, for any string similarity, I mean, even with the pairwise comparison, we were using a normalized edit distance. And this normalized is divided actually by the length of the string. So for larger string, we have this problem for sure. But I mean, sometimes it's inevitable to face these issues.
There's been a lot of research on that stage. In the early stage of the stage, people have to struggle with the instability aspect of the stage. Just in the spark vector with spark or just small, they have a lot of difficulties, but over time, it improves so much that there's a implementation that is being used there is pretty stable and pretty
Are there any cases where two foods have identical words and in different orders?
Yeah, actually, it was taken care of by this normalization in the sort by words. So based on the first letter of each word, they have been sorted. For example, you can see that here, rather than having Subway, meatball, sandwich, footlong, we have the whole string being sorted, and that's why it's not making so much sense. It's like footlong, meatball, sandwich, Subway.
So like sweet potato fried and fried sweet potato.
They're
both
referring
would be considered the same.
exactly. They're going to end up with the same cluster. And the reason was for the crowdsourced data, we had cases that the user put the description into the brand and brand description and just having reverse orders for the words in the string. So we had to deal with all of them, and I mean that was like the earliest efforts that we made in order to make them referring to the same entity.
But what if they're actually different entities? The same
Oh,
words?
so can
The
you?
order matters. In my counterexample, the order actually is fundamental.
Oh, okay. So in those cases, the worst case would be one of these entities, one of these words, they're not going to present a verified food. I mean, the verified food would be corresponding to only one of them, which is like. But by the end of the day, since we picked a cluster representative, the right order with the right nutrition information would be selected.
I think one thing you might have been referring to is that you could actually have two different foods combined in the same cluster. Arrogance,
True.
Because you're sorting by word.
Exactly. Yeah. So in that case, yeah, as I said, the concern was if we have two different entities that are ending up in the same cluster. So in that case, the worst case scenario would be there won't be any verified food from this cluster, or if there is, only one of these foods are going to have a verified food version, and the other one is not going to show up because when we have this voting scheme in place, I mean that vote is not going to be counted because it's like the calorie information is like different.
So clustering can be noisy by nature, right? But because of this popularity and memory voting based scheme, all this noise is going to be automatically eliminated if you have enough data. Right? So this is like this, if you have a lot of data processing, right? So it's going to be noisy, but that noise will be removed once we apply this kind of memory voting. And then two more will be reduced.
So the question was if we have translations to other countries. We didn't explicitly translate foods, but the same framework, the same algorithm was independent of the fact that the words are English. So that was the case for any non-English characters. So we ended up with a population of non-English food items that have been verified. Since we have lots of non-English foods in our database, like there were like enough number of them sometimes that could promote to a verified food. So we had some items, but we didn't have an explicit translation on top of each verified food.
Kind of a blue sky question. Granted, we don't have any kind of like perfect accuracy in the data that users give your application. But say if you had sufficiently accurate data, what are some of the interesting research-esque questions that you guys are interested in? And one of the reasons why I came to this meetup is given the foods, right? Given particular as they call them, macro ratios and people reporting on their body fats and their weights. With enough data and of sufficient quality, you guys could almost begin to publish research on what particular ratios of fats, carbs, and proteins happen to result in weight loss. Now, granted, I don't think you guys have any kind of like genetic information or anything like that, but there could be some interesting information that you can get out of it. So what are some of the really interesting questions with sufficiently accurate data that you guys are after?
That was a very good question, and it was too long for me to repeat. I tried to repeat some part of it. So the question was, if we assume that, for example, food information that we have in our database and the food log events coming in from users, what are the potential fields to do researches for the users for weight loss or weight gain or food habits and this kind of stuff? So that's, as a data scientist, these are the really exciting projects that I can work on. And especially as Chul mentioned, after being acquired by UnderArmour, we are now joined with Map My Fitness app, which is like a map to keep track of exercises by the users. So now we have two very general sources of data, the nutrition and the exercises. And of course, there are a lot of relations between them. So that's something that's actually the main focus of the entire team working on. And as you said, that's based on the strong assumption that the data that is coming in is not noisy, which is not a good assumption in general. But there are a lot of classification, a lot of recommendation, etc., has been going on. For instance, in this year's Spark Summit in San Francisco, another teammate in MyFitnessPal presented a method for recommendation using Spark for our food database based on the user's food consumption history. So there are all sorts of these data analysis we can do, and there are so many researches can be performed on top of this data for sure.
Just on top of that, are you guys gathering accelerometer data from the phone?
Sorry, can you repeat?
Accelerometer data from the phone in the app. Are you guys gathering that?
I think so. Yeah. Yeah.
That would be a really good indicator, that to match that up to the amount of time you spend exercising. Yeah.
Definitely.
So we are
exactly.
So yeah, after it's definitely so if you're interested in those kind of questions, then you should consider it.
Exactly. Yeah, sure. Any other questions?
Do you do any kind of error propagation analysis or accuracy analysis? By the time nutrition went created, maybe 70%.
The question was. Oh, okay. The question was if we have some kind of error estimation on top of it. So it's really hard to have this in place for the items, as you said, for the items whose nutrition information are publicly available. It's pretty straightforward, but this is not necessarily the case. And the nutrition facts for popular brands may change over time. So users have entered McDonald's burger 2 years ago, but it's different now from 2 years ago. So that's really challenging, but we try to use as much user signals as possible in order to evaluate. So for instance, if we keep presenting this food to the user and it's not selected or logged frequently, we realize that this is not probably a good quality. So we can probably take this out from the verified food list. Any other questions? All right, thank you so much.